So I wanted you all to have an opportunity to see this. Since I had access to it, I thought this would be really cool. The idea is that obviously you can see with a 180-degree screen that there's some opportunities for visualization that could take place in here that wouldn't be able to take place in other ways. And because you're engineers, you'll note there are 8 projectors. And the way the projectors work is this is just one large computer screen, just the same as any other computer screen. And they project such that they overlap a little bit. So like maybe this region right here is a region where both of those projectors are there. So when you design the PowerPoint, and I was given a template for a PowerPoint slide, and they show you on the template where the regions of overlap are, because you don't want to put critical things there in case there's blurring or something like that. So let me show you what it looks like. So I designed this one. These are engineering related things. I put them up here to give you sort of a quick assessment of how you can visualize different things here. So this is the plant that inspired the development of Velcro. So I don't know if you knew that Velcro was a guy was walking his dog in Scotland and kept getting burrs on his socks. And so when you look at these burrs, you can see there are sort of twisty little hook-like things there. And that's exactly how this works. These are basically just nylon loops that have been cut to form 2 hooks. And then this is just a bunch of loops. So that's exactly how the burr sticks to the sock. This is some sand on a shell. And I don't know what that is. It just came with it. I picked this up off the beach and took a picture with my microscope. But it's kind of cool. This is an LED. So you can see this is where the chip is in here. This is, I don't remember which Greek temple it is. It's a Greek temple, right? But this is kind of interesting from a civil engineering perspective. This is a couple of examples of textiles up close so that you can show different weaving patterns in a way that you'd never be able to appreciate. Also, if you think about it, even if you show on a screen that's smaller, someone who's visually impaired is probably not going to be able to see the detail that you can show them here. And of course, it's really neat to have a video embedded. And this video is in Costa Rica. If you watch, that's a blue morpho butterfly, and it's designed to do exactly what you see here, right? You see nothing, 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 then suddenly these bright blue flashes. And I've been fascinated with blue morpho butterflies for a long time because they thought that the reason that they were so bright blue like that is that they had LED-like structures on their wings. And now they know that is not why they flash like that. Now they are able to actually get close enough up views of the blue morpho butterfly scales. When you get a little close and you begin to see it's not as bright blue here, and then when you get this close, you see that the scales are actually transparent. And then you take an even closer picture and you realize that the scales have nanostructures on them that are very effective at reflecting blue light. So it's not an LED, it's just a nanostructure that reflects blue light to make it look like that. Which is pretty cool if you think about it from an engineering perspective. This is a close-up of a garnet crystal in a rock to sort of examine crystalline structures. This is a picture of a leaf. It's blurrier than I wanted it to be, probably because I didn't record it in as high quality as I needed to do this. But I was fascinated with as leaves are changing colors, can you actually show you some of the visualization possibilities that you can do. And this is just a simple PowerPoint slide, very large PowerPoint slide with things. Oops. So another example, this is a slide that I made for that previous presentation that shows the 14 grand challenges for engineering. But today's topic, so how many of you are familiar with electromagnetic radiation? In what ways are you familiar with it? She's like, I'm not answering now. I was answering. It's the other guys who answer. I can see your face. I know you. I do the same thing. What? How have you heard of electromagnetic radiation?
In my undergrad, like I studied communication as well.
Okay.
Communication technology, so like you have to know which band is used for like which communication, like for radio or for like mobile devices for 5G.
Okay, so like 5G or for mobile devices or something like that, right?
And how to like transmit information through the ear. So,
Okay. All right, good. What else how else have you heard of electromagnetic radiation?
I took class regarding water physics.
Okay, all right, so you learned about this. The thing that I first of all, I love electromagnetics, but aside from that, this used to be the realm of the engineer, right? And it used to, particularly the electrical engineer, and it maybe people understood that radio communication used something, right? That there's megahertz and kilohertz on your radio dial. So maybe they understood that, but very, very few people would have made any connection between radio waves and visible light, right? Or X-rays. People know what X-rays are because they go to the dentist, they get an X-ray or something like that. Very few people would have realized that they're all part of a similar kind of thing. Except now, well, we do have microwaves, but we understand infrared because infrared is used by your television remote control. And if you've never done this, you should try it. If you look into the remote control, this won't hurt you. If you look into the remote control, you won't be able to see anything when you press the buttons. But if you shine it in the camera of your cell phone or your iPad, it will. You'll be able to see the flash. Because, and in my case, one of the cameras, because I've got a front-facing and a back-facing camera on my iPhone, one of them can see it and the other one can't. So it's interesting. The camera that's not on the screen side, I call that the back-facing camera, can detect the infrared radiation, whereas the other one can't. And that's kind of interesting, right? But people have gotten a little bit more. This has entered the lexicon a little bit more than it ever had before. So if you're an electrical engineer, you would have studied that, and then you would have studied the equations that describe, that are the basis for all of electromagnetics, electric current, everything. And for those of you that don't know, these are Maxwell's equations. And one of the things about Maxwell's equations is that they look scary, particularly for an undergraduate who may never have even seen the operators, much less equations like this, but they are the four most fundamental equations behind all of electrical engineering. And so we teach them in electrical engineering, but the way they're typically taught, the way they were taught to me in electrical engineering is, these are Maxwell's equations. This is how you calculate things. This is a curl. This is a partial derivative with respect to time. Now let's do some examples. Here's a function. functioned, et cetera, right? And here's your electromagnetic, or here's your electric field, calculate your magnetic field. Here's your magnetic field, calculate your electric field, et cetera, et cetera. And so I learned how to manipulate the math, but it's taught as a math class, right? And so a lot of people are turned off of electrical engineering because they're frightened of the math. And it does look scary if you don't know what it is, and if you have any sort of doubts about math in general, because as you know, the general population, if you walk outside there and ask, hey, is anybody out here afraid of math? So they will immediately, there will be many people that will say that they are afraid of math. There are people that say they don't want to be engineers because I can't do math. Like, well, it's not true. There's nobody that can't do math. Everyone can learn it. Not everyone can teach it. So I thought I'll explain Maxwell's equations to you today. We'll see if this works. Now those of you that already have had classes in this, you better understand, but if you haven't, maybe this will be different. So I started out by just taking the equations, first of all, and just sort of explaining things, right? So there are first of all some variables. So there's a magnetic field and there's an electric field. Time, so we're assuming that these things might change in time. There's a current, J stands for a current, but not a linear current on a wire, current spread out over a surface, okay? And then there's a couple of operators. So here's the del cross operator. There's a del dot operator. And we'll figure out what those are in a minute, okay? Again, the electric field shows up. Here's another thing. This is charge, like current, but just sitting still. And it's spread out over an area. So what else have we got? Well, we got epsilon, that's just a material constant. Material constant, mu is a material constant. So there's some number. These all look familiar. That looks familiar, great. Okay, so these are some equations with some variables in them, fine. What they describe is behavior. They model the behavior of these things called electric and magnetic fields. Now, most of us aren't born knowing what electric and magnetic fields are, right? These are a couple of pictures of electric and magnetic fields. That one's not great, but again, you get in here and you discover the one thing about blowing up something 100 times is that you better practice, because you don't know what it's going to look like when you put it up there. But the words aren't important; the pictures are more important for us today. So, what is this? This picture. This is a coil of wire. Okay? The green represents a magnetic field. Whatever that is, we still don't know what that is, but whatever it is. And this implies something about some electricity being generated. This is a coil of wire. A lot of wire. It's simply wrapped around a piece of PVC pipe. And I took an LED and connected it to the two ends of the coil of wire. This is my current detector. I'm gonna use this to detect whether I'm generating any electric current or not. Now to get the magnetic field, can you tell me something that might generate an electromagnetic field? I mean, a magnetic field that you might be familiar with? A magnet, right? Doesn't that make sense? So, let me see, a magnet. Oh wait, here's a magnet. So here's a magnet. invisible. So I'm going to get something magnetic and put near the magnet. Now, will you hold the glass, please? So these are iron filings, which iron is magnetic, right? So I'm gonna take the iron filings and sprinkle them on the glass plate. I could sprinkle them directly on a magnet, but I will tell you from personal experience that it makes a mess. And I'm trying not to make a mess. Yeah, come on. Thank you. Because the process is as interesting as the Now what you see is that the iron filings are lining up, right? There's structure there. And it turns out that the way the iron filings behave, they line up along the magnetic field lines. If you look at that picture there, it looks similar to this, doesn't it? So the magnetic field lines are generated around the magnet. So that's what a magnetic field looks like, kind of. So, good, you're just in time. Actually, you've seen this part before.
Oh, I've seen this before. Okay, good.
Not all of it, but you've seen this part before. So now that maybe we have a little bit of understanding about a magnetic field, let's see what we can do to use that magnetic field. So, and you've probably played with magnets before, right? Right, you know that they have attract and repel behaviors, right? So you've been playing with the magnetic field, you just didn't realize that's what you would do. So now let me take this magnetic field that this magnet is generating, and here's my coil of wire, like that coil of wire in the picture there. And the magnetic field that we just visualized here will represent the green lines. So I'm going to put that inside my coil. Now you see why the PVC pipe is here, to make it easy to keep it inside the thing where I want it. Okay, well, I'm just going to hold it too. I'm going to put my thumb on the... So this, just in case you wonder, this is a coated wire. So where I made the connection between the wire and the LED, I removed the coating. But when I touch the LED wire to this part, it's still coated, so there's no connection that's made. This takes more manual dexterity than I apparently have today. Seriously? Okay. So what happens? So when the magnetic field is still, the LED is not lit, so there's no current in the wire. But when I move the magnetic field by just sliding it up and down in the wire, there's a current generated, and I can tell because it lights the LED. And it doesn't matter which direction it moves. You notice that? Which is interesting to an electrical engineer who knows that an LED actually only works in one direction. If I were to hook up a battery to it, it would work in one direction and would not work in the other direction. But this way, it doesn't matter which way I'm sliding. It still works. That means the current's always flowing the same way, whether the magnet is going this way or this way, which is interesting. And the thing is, let me think about this. Let's see if we can phrase what's going on here. So I have a magnetic field, and I'm changing it over space, right? I'm moving it. So 1 minute it's here, 1 minute it's here, 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 here. the magnetic field is changing over space because I'm moving it. You buy that? I'm looking at your eyes, make sure you're actually moving it. It's changing over space. So a spatially varying magnetic field gives us a current. Huh. Oh my gosh. So I said that without explaining the math, this operator calculates how a field varies over space. So this would be a magnetic field that varies over space. It'll be 0 if there is no varying over space. It'll be non-zero if there is varying over space. This gives us a current. Oh, it's something else. It gives us an electric field that varies over time. Problem is that just like the magnetic field, we can't see the electric field. The only reason we can see the current is that I used a current detector, the LED, right? So there's also an electric field there. Now, electric fields can't be seen either, just like magnetic fields can't be seen. But I can generate an electric field, and I can use a similar detector to show you what an electric field too. So this is a coil of wire, just like that coil of wire, okay? But this time, I'm going to get my electricity from plugging it in. So what will happen is that I will plug this in, electricity, this is a complete coil. It starts, that's what I do, I think you can get it. Here it goes, thank you. So if you can visualize it like this. Electricity comes in, current comes in, 1, goes all the way, wraps up, and then this is a continuous wire, so it wraps all the way back down and comes out the other side for a complete circuit. Okay. Sometimes I forget the age of the people I'm talking about and use different terms, so sorry. Thank you. That's good. That'll be much faster than making me get down and back up. Okay, so voila. So the current is flowing. Now what you hear is not got anything to do with the electric field, because it turns out that what's in there is a very large capacitor to boost the voltage, and it sparks inside there. So that's a little spark that's probably not desirable, but you know, you pay $250 and this is what you get. Okay? So just like the magnet generated a magnetic field, which we detected with that, let's see if this can detect an electric field. I don't see anything moving, do you? So instead, what I will use is here, a fluorescent light bulb. Because fluorescent light bulbs work by having, this is just a tube filled with probably nitrogen gas and some powder on the outside to make the light visible in the right color that we want it to be. And basically what you do is you put an electric field around this gas, and the gas emits photons, which I can go into the chemistry explanation, but that's not what we're here about, right? So that's how all fluorescent light bulbs work. So if I take this and put it in the electric field, it'll behave as we expected it to, so this detects electric fields. It does not detect magnetic fields. This has a magnetic field, that has an electric field. When it's sitting still, this magnetic field is not varying in space or time. This electric field this is just a straight DC current. So this AC coming out of there, it's being converted, so there's no change in space or time either. So this is an electric field. So if this electric field varied over space, then what we would get would be a time-varying magnetic field. So maybe if I took that device and moved it around, it would be creating a magnetic field, but I haven't figured out any way to show you that. Except for do it and have somebody throw iron filings at me, but I'm not interested in trying that to see if it works. Okay? So, electric fields, magnetic fields. A magnetic field changing over space yields a current in a time-varying electric field. There are 4 other equations over here. Notice this. So this is that the del dot is also an operator that tells you how a field varies over space. Just a little bit different than the del cross tells you how it varies over space, but this is also a spatially varying. So this says that a spatial varying magnetic field gives you 0. This one looks a lot like that one over there. An electric field that varies according to this over space gives you a charge. But a magnetic field that varies over space does not give you a charge. Why? A charge. What is a charge? When current flows, what's it made out of, or what carries the energy of it? An electron, right? A piece of an atom. Atoms have 2 pieces that I think about, positive pieces and negative pieces. The others are, let the quantum electron people worry about those. The positive pieces and the negative pieces. You can strip off the negative pieces of an atom and move them around and make them do work for you. That's a charge. This says that you can't do that with magnetic things. It says there is no such thing as magnetic charge. So if you thought of a magnetic, you can think of any atom as having this positive piece and this negative piece, right? And every magnetic bit, little tiny, think of an infinitely small magnet, also has a positive side and a negative side, a north and a south pole, right? But for magnets, you can't strip those apart. Every magnet has both sides, but we don't know how to strip it apart. So there are magnetic dipoles. There is no magnetic monopole, which would represent a magnetic charge. Does that make sense? That's what that says. So this is the math. So you can look at, so this is just the nomenclature. So they're saying take this function f, and we're going to define it as a 3-dimensional vector function. And I hat, j hat, and k hat are the three directions. That was harder than it should have been, right? And then the del operator can be abbreviated as a derivative or a partial derivative along a particular direction of the vector. If I were a mathematician, would probably be fainting at this point, but I'm definitely speaking engineer speak now. So then, when you do this del dot, which is called the divergence, what you do is this operator operates on the I, so the I part of the operator operates on the I part of the function. The J part of the operator operates on the J part, et cetera, right? And this gives you a scalar. So the vector has disappeared from that. The del cross part, which is called a curl, is doing this, taking the determinant of this matrix. So if you get these unit vectors here, yeah, that's right, unit vectors. The partial derivative operators in the pieces of the function that correspond to each of those unit vectors, and then you take the determinant of the matrix, you get a vector with an I, J, and K part. Okay? So how does this being the math, translate to the things that we're pulling? So for the del dot thing, this is how the function varies in the x direction. This is how the function varies in the y direction. This is how the function, it's not just how it varies, right? It's the rate at which it varies in the x direction, the rate at which it varies in the y direction, the rate at which it varies in the z direction. Add those up. So when we're taking del dot something, the way sum those three types of variations, and it gives you a charge spread out over the area. Or in this case, the three types of variations are going to have to sum to 0. So if one of them is varying this way and the other is varying that way, it's got to, all the components end up having to sum to 0. If that makes sense. All right, that's not that complicated. Now these over here, yeah, question.
It's not a question, it's more of a comment.
Oh, good, comment.
It's been, what, 9 years since I took Calculus 3, and now I finally know who to blame for them forcing me to learn what curl is? It's you.
I'm going to totally bring it around to the other disciplines in just a minute.
You use curl.
No, you don't. You're right.
But the fact that I don't use it and I still remember it because it scarred me so badly should be telling.
But when you
Even-
were taught it, were you taught like this?
No. I mean,
Yeah. So the curl is going to give you the component that ends up in the y direction, the x. Let's call those x, y, and z instead of I, j, and k because I'm going to do that anyway. So the component that ends up in the x direction for the curl vector has to do with the way that the y and z direction things varied on their original axes, etc. Okay? So this is not along a line, which is sort of how the divergence was, along a line, because each of the components matched up. This is some sort of crossing type thing. In fact, it's some sort of curling type thing that's going on. So what we're ending up with is an understanding of how this function varies around a point. That's what this enables us to calculate. So this isn't just varying in space, this is it varying around a point, okay? And then that gives you the time varying electromagnetic field, or the way the electric field varies around a point gives you the time varying magnetic field. Is that math kind of okay? That's the math? But I'm still not quite getting it. So I want to see a little more. So what is curl? What is divergence? The moon has nothing to do with it. I just really like this picture in here. I thought it was fun to do this also. So that's why. Oh, I don't have to do that. I have it right here. Exercise if I do that. So no, there I have to go back there. Find it. No, that's shouldn't. I need the mouse. Oops. There it is. Let's do divergence first. Lost the mouse. There you go. Okay. idea of how, that's not it either. This is it. So here's, if you have this point in the middle, this is how a field might diverge from the point. So this would calculate a positive divergence because the function's varying directly away from the point in all areas. And they put a ball in there just to show you that nothing moves. If these arrows were pointing toward the center, that would be a negative divergence, which this is like expansion. A negative divergence is like compression. So if you have an electric field that's expanding out from a point, like an antenna, that's what this looks like. Or if it's the other way, it's like a compression, which I'll show you in a minute what that might look like. So that's that. Now contrast that with curl.
So that was for the electric field?
Or magnetic field, either one.
Okay.
Yeah. We'll
But
go back to the equations in just a minute.
Okay, but a magnetic field would have to be neutral, right? Its divergence can be positive?
It'll have to sum to zero. So all those little vectors of a magnetic field would have to sum to zero. You're right.
Okay.
Thank you. Sorry, I didn't understand the implication of your question. So curl is measuring how the function varies around an area like that. So this one has a curl that'll result in a positive variation because it's uniformly varying like this around the center. Yeah. And in fact, you've maybe heard of something called the right-hand rule. The right-hand rule was developed as a way for you to visualize how the direction that adding up all these things would give you. So you wrap your hand around and then you're going to get a positive curl in that direction. In the case of this right here, this is how the current varies. Or this is how, if the field varies this way, the current's going to vary around like that. So I started with my thumb by varying the field that way, and then I should get a current, so the current should go around this, which it does, right? That's why we have to have a loop of wire to generate a current. A straight wire won't generate a current. I have to have a loop of wire because of the math. Or a loop of wire behaves this way, and we can model it by that math, which is what's really going on. Does that help a little bit? A little bit? Now, looking back here, if you have an electric field that's diverging, you'll get a positive charge. If you have an electric field that's converging, you'll get a negative charge. Okay, we can deal with that. We know what positive and negative charges are, right? I forgot to bring a balloon. Imagine I'm rubbing a balloon on my head, and I'm collecting negative charges on the balloon because it's stripping off electrons off my hair, okay? Negative charges, positive charges. The absence of an electron is like a positive charge. Electrical engineers pretend like there are positive and negative charges running around. They kind of are. But like you said, in the case of the magnetic field, it's gonna all sum to zero. Can't get a commitment. For this one, like I said before, if we take the curl of the changing magnetic field, we end up with a current in a particular direction. It's spread over an area, it's spread across the width of that wire. It's not just in a line in the wire, it's spread over the whole wire. And we get an electric field that's changing in time, but we have no way of detecting it. Same thing here, an electric field changing in space like so should yield a magnetic field that changes in time. So a current in a wire moves because of an electric field. So here's some wire that's curled, okay? So if I pass current through this, I'll have an electric field curled around a central point, right? So that ought to yield a time-varying magnetic field. So if I put a magnet in the middle of this wire, then the magnetic field of the wire that the wire is generating will be changing over time. That means that the magnetic field of my fixed magnet in the middle will respond, right? If this changes, if the north and south poles are pointing like this, then the magnet will line up like that. If they move like this, which because of the way that I have this thing coiled, it does, then it actually pushes the magnet around. And that's actually how motors work. There's a magnet inside the central core. I put electricity through this. I generate that curling magnetic or electric field, and that generates a time-varying magnetic field, which forces the magnet that's attached to this case, this is a blender motor, which is attached to the blender things, makes it turn. Does that make sense? Now the thing that's a little confusing sometimes, if you look at this demo or you look at this demo, in both of those demos, I've got fields and I've got currents, okay? So how do I know which one of these applies? For that one versus that one, it's easy to know which one applies, right? Because in this case, I've just got fields, just an electric, just a magnetic. But in this case, it's hard to determine which one applies. The answer to the question is it doesn't matter. Because they're 100% analogous. If I generate a magnetic field and move it around, I look at it as I'm starting here, right? That's the left-hand side of the equation, that kind of makes sense. Then I'm going to get out a current and an electric field. In this case, if I generate an electric field, which I can call the current in the wire, then I'm going to get out a magnetic field that varies in time. Why isn't this 100% analogous? Why is there not a J thing over here? Because there's no magnetic charge. It would be a magnetic current, but there is no magnetic current because there is nothing to carry it. Other than that, they're all 100% analogous to each other.
So would that equation technically have a component that is generating current, it's just that it sums to zero so we don't include the component, or?
No, the current is involved in this electromagnetic field. We're realizing the current as an electric field instead of calling it out as a current.
Oh, I mean on the magnetic field side, the magnetic current we were talking about.
No.
Is it because the component doesn't exist, or it's mathematically not
It
contributing?
doesn't exist, so it doesn't sum to zero. That's a great question. Yeah, so there's nothing there that's summing to zero. It just literally doesn't exist. at least that we've found. If you want to do unified field theories, then you might want to be looking for magnetic currents. Now, if you're not an electrical engineer, and the point of the micro-teach was to demonstrate a way to sort of give people an idea of a hard subject. Maxwell's equations can be viewed as a hard to understand subject. Oh, I forgot I had those up there. We don't need them. Okay. But these things apply also in other places. So for example, suppose you want to understand fluid flow. This is an example of fluid flow in the atmosphere. These are atmospheric, or no, these aren't atmospheric. This is water currents. These are water currents along the coast. It looks like Japan.
That is Japan.
What?
That is Japan.
Okay.
You can see Korea on the
Okay, good. So that's Japan. These are water currents, cold and warm water currents. And they have a curl, don't they? So there's pressure generated. So if you want to understand the effects of currents, say, on erosion or something else, you can use this similar equations to Maxwell. So divergence and curl are things that apply. I'm not getting a current, I'm getting a pressure. Or a force, probably. Well, pressure is cool. Okay. I'm an electrical engineer. I just take these parts with a grain of salt. Okay? So this is just one application. If you want to understand climatology, currents, you could do it. Similar air currents would have a similar thing.
Shows up in solid mechanics all the time.
Oh, you do?
Yeah, divergent and curl, you end up seeing that in like how you end up calculating out like stress and strain for like a change in material and things.
Yeah, so they're modeling exactly the same thing as they are in Maxwell's equations. It's a way of modeling a behavior like this. And then we end with pictures of bees, bugs, because I like them. So that's it. What do you think? So going back to break down what I tried to put together for you all, whether I did a good job or not is the question. I tried to take something, so first relate to your experience, right? Then say, okay, typically it's taught as just this, but I modeled reading an equation with words, right? So each one of these, and I didn't point this out before, but has a sentence at the top that reads the equations with words. And all equations can be read with words, but we don't often do that. And if you can read it with words, you can understand what it's modeling. So that's part of this lesson, modeling that. And then translating, trying to show how the math is modeling actual physical phenomena in pictures, then in demonstrations that we're supposed to connect immediately to the pictures in your mind. Then to go back to the math and understand the machinations of how you do the math, right? Because this is ultimately, if I want to know how much current I can generate with that magnet, or take it apart and actually just use one magnet. I just thought of this. This would actually be interesting to know, because in theory, if I just use one of these magnets, I'm not going to be able to show you. Just warning. Hold very tightly to them, because if they
Pinch.
snap back together, it hurts like a lot.
Oh well.
Yeah. As soon as you get it apart, jerk it apart and give me one.
It does not want to move.
These are
Anyone
very,
else wanna
very
try?
strong magnets. Anybody else feeling strong?
I can snap them, but I can't pull
I
it
gave you
apart.
the warning, right? Don't let it snap back together. If we can't do it, it's okay. I just was curious.
These neodymium magnets,
They are, so they're very
Yeah.
fragile.
I've also broke.
I break them all the time. That one's already broken. I broke it yesterday. Good, good. All right, yay. So we get this as far away from him as possible. So now let's try this with one. You saw it was pretty bright with two, right? In theory, the result of which one was it? That one. The result of that equation should be smaller numbers, right? Because the magnetic field is smaller. So let's try it and see what happens. Unless I broke it off, which I did. Sorry, I'm pulling the enamel off just to make sure I get some connection. The reason to use this real thin wire is that you can wrap up 300 turns and it's not huge and it's not heavy, but it's also very, very fragile. Right. Oh, no, that looks pretty bright to me. Maybe, can't see the difference. Okay, well, it's worth a try. So, connecting the math to the physical things, right? So I did the physical things in the middle so that you had something to be thinking about when you were thinking about this. And then we looked at the applets to try to help you visualize the math a little bit more, whether that worked or not, I don't know. And then reminded you what we were doing, and then showed you another application of the same type of math to hopefully maybe build it even further. That was how I put the class together, or the presentation together. So, and then you concluded with something that I like, that's all. So there you go. Anybody want to play with me? If you want to play with it, okay, it's fun.
What are those things called where you like draw, not an etch-a-sketch, but the similar where you draw a face with it?
Yeah, yeah, so what you're doing with that is, what you're doing with the thing where you've got iron filings underneath a plastic usually. And when you run the magnet over it, it temporarily magnetizes the iron filings. And then you demagnetize it and they fall back down. So are you magnetizing the iron filings or are you magnetizing the plastic? I'm not sure. You might be magnetizing the plastic thing. And then when you run the magnet over it, it demagnetizes it. That could be what's happening. I never thought of that. And that's a really cool phenomenon that is useful. I didn't bring this whole setup, but you got to see it one time. But that's how electric guitars work. Same way. Because for an electric guitar,